A brief overview of the Doppler effect. You've all heard of this phenomena either directly or indirectly. Perhaps you're at a racetrack and here comes the high-pitched race car coming toward you and then away. Something like that. And obviously there's a change in the tone of the sound as it approaches you and then moves away from you. Well, that's very explicable from the standpoint that the speed of sound is a constant in the air. So these represent the waves of the sound coming from this source. So here's a fire engine coming along. And as it's producing the sound, each subsequent wave that's produced, since it's moving, it shortens the distance between them. So they get scrunched up. So the observer over here is hearing these crests come by his ear faster at a higher frequency, a greater rate at which the crests hit his eardrum, and that increases the pitch. Since they're produced as he's moving away from this observer, they're stretched out, and this person, the waves are coming at the same speed, but they're spread out in distance and therefore in time, and therefore the tone goes down. So that's the basic idea behind it. The same thing holds true for light. So here is a source of light, and if it's moving toward this observer, the light waves get scrunched up or spread out. If they get scrunched up, that's making the waves shorter, and shorter wavelengths are moved toward the blue. If they get spread out, the longer wavelengths are being stretched out and redshifted. So we have redshift and blue shift. And so that's it in a nutshell. And if you want to specify how much that is, this is a little basic mathematical relationship. It's the change in the wavelength, how much it's changed, divided by the original wavelength without it being shifted. That ratio is equal to how fast the source is moving compared to the speed of light. Kind of makes sense. So those are the various quantities I just mentioned. And so it's easy to plug numbers in and find out the unknown with a formula like this. How would this work for seeing the amount of shift in the spectrum of, say, a star as a result of motion? Well, here's how we can think of that. This is showing the alpha, the Balmer alpha line in Arcturus, that red line, 656 point some nanometers. And this is the laboratory wavelength for the emission line of hydrogen, as we've been talking about. Now this is the absorption line for that particular wavelength, which isn't quite as neat as a superfine line, but that's the absorption line. It's spread out a little bit. But why is it shifted like that? Well, it's because of the motion of Earth toward the star Arcturus, which is where this spectrum is from. So sometimes we're moving toward and sometimes away from the star. And so here's the speed at which we're moving by observing the shift in the spectrum. The shift in the absorption line specifically, we can calculate what the velocity of the Earth is toward or away from the star. So there it is, and from a conceptual standpoint, this is what it looks like. So there's the change in the wavelength toward the blue as Earth is moving toward, and the change in the wavelength toward the red as it's moving away. So this little tiny bit of change in wavelength, it's a small change, it's a fraction of a single nanometer compared to 656. So it's not all that fast compared to the speed of light. Red shifting, it's a shift toward the red because it's a shift toward a longer wavelength. So that's where the peak of this absorption line is. Peak is over here. So you see a blue shift and a red shift. So that's the Doppler shift, and you can quantize it. You can quantify it, I should say, with these careful measurements of the spectrum. And now this idea of Doppler can also be used to understand the motion of stars, even their rotation. So let's consider how this would work with rotation. So here we see a star rotating, and what this is going to produce is, well, if you're observing the spectrum of the star and the material is coming toward you, you know, it blue shifts. If the material is moving away from you, it red shifts. And this is you could say, the intensity of the light It could be an emission or an absorption band. And it's fairly narrow, but it has some width, and partly because here's the line itself, the unshifted line, if you just look at the sun. And when it's moving away from you, it's red shifted, so it goes to lower wavelength, and blue shifted, higher wavelength. So as we look at the spectra of the star, we see this absorption or emission band. It's usually an absorption band. It just looks like it's the wrong way here, but that's okay. But it's spread out a little bit because of the blue shift and red shift. It widens, it broadens the spectral lines. That's what it's called. By the same token, if it's moving faster, then it's blue shifted more and red shifted more, and so there's the greater red shift, the greater blue shift, and the entire absorption line is spread out even more. So based on the width of the line, you can get an understanding of the relative rotational rate of the star. Isn't that amazing? Conceptually, if you have two stars orbiting each other, it's a binary star, you could see that one star coming toward you, light's blue shifted, the other star moving away is red shifted, and you can determine that by seeing those relative red and blue shifts in the spectra. So a very useful phenomena for astronomers. Something called the proper motion of stars. Well, what we have here is from Earth looking line of sight to a star. Any radial velocity will show up as a Doppler effect because that's either moving away or moving toward. But a transverse velocity will not pick that up because, well, the distance, the motion toward or away from the observer is zilch because it's transverse. So usually both components are there, and you have to observe positions of the star over a period of time, and you can get the actual velocity by combining the radial and the transverse to get the proper motion or actual velocity of the star in the sky. And as a summary of the results that you get, so here's again showing the Balmer line series. In the laboratory, we have the emission lines, we have the emission spectrum here. If the object is being red shifted, you see all the lines shifted toward the red. If it's moving even faster, the lines are shifted more to the red. Notice that the colors are actually changing here. If it's blue shifted compared to the original, this is blue shifted. Everything's moved to the left or to the blue end. And then even more, the blue is actually turning violet, etc. You get a greater blue shift. So again, careful analysis and measurement of these quantities, we can determine the speeds and the information about the motion of various celestial entities. The search for extrasolar planets has really taken off. The traditional primary way to discover the existence of a planet is not to view it directly, because the parent star is typically 1 billion times brighter and totally washes out any light we might see from the planet directly. But we can observe the motion of the parent star, and actually it's the disturbance to its motion, because if a planet is orbiting around the parent star, it's going to put a gravitational tug on that star and shift it back and forth. So we can observe the motion of the parent star back and forth, toward us, away from us, toward us, away from us, producing a Doppler shift. That can be translated from as a plus or minus velocity with respect to the standard. Okay, and so taking a bunch of data, if you can fit the data, here's all these blue dots are data taken over a period of years. If you can fit that data to a sine curve, which is the kind of curve you get if you map the motion of that back and forth motion, if you can map that with respect to time, it'll produce a sinusoidal graph. And when you see the sinusoid that fits the data the best, you've actually determined the period of the orbit, and other things fall into place from there. So that's how you detect planets moving around other star systems that you can't image directly. That'll wrap it up for the Doppler effect, and hope you learned a little bit from this lesson.